Hello, everyone. Just wait a couple of seconds here. More people to join. Let me open this. Okay. Can you tell me if you can see the screen, like the slides, please? Okay, perfect. Thank you. How is everyone doing? More exams this week, or it's over? Okay. Yeah, more. Wow. Very good luck. Depressed. Everybody's depressed, Andrew. Like yeah, I don't know. It's getting slightly, hopeful, but I hope things will get better as spring is coming. So yeah, yeah, but it will never get better, and I don't want to, I don't want to disappoint you, but I remember those days when I was student and I only had one main objective, just to pass the courses and just so it's much easier than dealing with life issues, work, job, family, and other things. So anyway, try to enjoy as much as you can. Okay, guys, so I will get into the topic of today. Just before I start, I hope if anyone in the class sent me an email about the exam, like during the exam time, missing the PDF to be downloaded in the exam, or making sure those files are uploaded, errors in the submission, stuff like that, because it was an overwhelming number of emails. And I think the only way to respond to you is by checking first is that everything is okay. So I receive all the emails, so don't worry about it. I just get the TA to look into the folders, the files, and making sure that everything is okay. And then we'll send you an email confirming all outstanding issues. So please just be patient, and we're taking care of all the requests and so on, right? There's no major issue, just some technical problem people faced in the exam. Okay, so today we have a very, very interesting chapter, and I consider chapter 5 is a very important chapter in fluid mechanics subjects when it comes to design of systems. But also can serve other type of design, because in general, this chapter is called dimension analysis and similarity. And the similarity we're talking about here is when you design a system, or you design an object, or you design a device, and you try to build a prototype. And this prototype you test it and make sure that it's working, stuff like that. So it's very related to what you are doing, what you're going to do as a senior student in your 41X for some of the ideas. So I will consider this topic today is a core of core knowledge that is needed when you are actually building a new design, or testing an idea, for example. Okay, so I mentioned in chapter 3 that we have 3 ways of analyzing fluid flow in systems. The first one is the control volume approach. We look at a certain control volume for a system, and we are looking into what is coming in and what is going out, what the change of inside the system, and we apply the mass conservation, and we apply the momentum conservation as well. And then we move to chapter 4, which is we didn't cover 100%, we covered part of it. That is talking about different analysis that we deal with the fluid mechanics or fluid flow by looking at a small little element. Instead of a big control volume for the whole system, we look at a very small little control volumes. And now we have to introduce something called the differential form of the governing equation. So we look at, the conservation of mass and the conservation of momentum in the form of, differential equation in this case. We didn't get too much into the differential representation of the momentum equation, which is Navier-Stokes equation, which is somebody will try to expand his knowledge in fluid mechanics when he studied computational fluid mechanics and so on. We don't have time for this course to get into this, but at least we understand what is the flow field, how can we describe the flow velocity and acceleration, and also look at the continuity equation in the differential flow. The third type of analysis is basically presented in this chapter 5, that is talking about, understanding the dimension or the economic value of the dimension analysis. Why engineers, especially engineers, right? Why engineer want to look at a different way of modeling, the fluid flow in this system using what we call a dimensional analysis. Okay. Also understanding one of the very famous method that is used in the dimensional analysis that's called Buckingham Pi theory, and finding the dimensionless group and numbers that is very commonly used in fluid mechanics, and could be also applied to any other subject. So I promise you that this is not only applied to fluid mechanics, but also applied to any other subject that is dealing with, prototyping or design and so on. And then we can get a little bit familiar with what we call it, the common dimensionless group numbers in fluid mechanics, especially, and then understand what is a similitude and similarity. Okay, when we are talking about modeling, or we're building a model for an actual device, what kind of similarity we're talking about here. Okay, so let me start with a similarity and similitude. Okay, so similitude is basically a theory of predicting prototype performance from a model observation. Simple, wording here, right? So we build a model, right? And we want to make sure that, how this model, will perform if we test it to represent the actual prototype performance. Okay, so basically, before we build, for example, what is given here, like for aeroplane, for example, or design, we're not going to build the aeroplane and then we just fly it and see what's going to happen, right? So what you're going to do is you're going to build a model, and this model could be a 2-scale model, could be the same size, could be even smaller size, and we test all conditions, angle of attack for the wings, the takeoff, the landing, everything we tested in the lab, right? Not only this for the whole aeroplane, but also the component inside the aeroplane, every piece of the, that we are basically, involved in this airplane total performance. Okay, or automotive, we're building the automobile, and then we can, or train, for example, we are building a scaled model, and we test this model in the lab, and we apply so many conditions just to make sure that before we design the full scale prototype, we tested in the lab. So in this case, it's unsolvable. Actually, it is solvable, Marcus. Not all the problem that is completely unsolvable, right? Of course, dimensional analysis, as I'm going to explain in a few seconds here, that it is very applied to when you have a very complex problem. You have so many complex parameters affecting each other. But even for a well-designed, solved problem, right? Sometimes you need to test this, right? Maybe the analytical model that you have is you don't know exactly. Navier-Stokes equation has a lot of assumptions, right? I like you thinking about that. So Navier-Stokes equation, computational fluid mechanics it has a lot of assumptions, right? Even though you think you are kind of modeling every single particle of the fluid movement around the car, you still have to calibrate the computational code, right? So I would have to say that lots of people doing computational fluid mechanics or even computational in general, right? I would, for someone like me, I came from an industrial background, and in the industry, we tend to be a little bit kind of skeptical about solution or results coming from a computational code or a computer simulation. Why? Because we have to make sure that we are not making the wrong investment or the wrong judgment. For example, in the nuclear power plant, right? You cannot afford to have like a simulation that is predicting the solution within 5-10% error, because these can lead to a catastrophic accident and so on. So it is all kind of relative, right? Depend on what kind of design that you are actually doing, right? What this design is used for, right? So you have to put what is allowable error that you can tolerate, and what kind of condition that you will test it, right? So sometimes even you design a device, or you design an equipment that is running at a certain condition, but now how about if this equipment is running outside of the design condition, right? So sometimes you need to know what is your limitation and what will be the extreme cases for this prototype if it's if it is finalized and used by end user and so on, right? So so all the computational Navier-Stokes equation, for example, it's for laminar flow, right? It added like some turbulence term, but this turbulence term is also models and assumptions, right? So all this is something that we needed the dimension analysis to do. Okay, so we'll learn in this chapter how we are doing this, and we're gonna apply it on a very simple problem. We agree that this course is basically introducing you to understanding big topics, right? Just at least from a fundamental perspective. You can expand this if you are, if you are interested to learn more about this. Okay. So the importance of dimension analysis, I'm repeating myself here, is like helping you with planning, presentation, and interpretation of experimental data. So you need to really test a model to see what will be the performance, or what is the anticipated performance of the prototype, and look at this experimental data and judge the performance. Okay, so the idea now, how can we really organize this data and and look at the effect of for example these parameters on the performance of this device? It can be overwhelming. Okay, how many number of data that you need to take or test in the lab before you actually decide, okay, this design is good or fit for service, it can actually get into a practical practical field. Okay, so it is very important. Dimension analysis, as I mentioned, is you will see this in variety of applications. Like you can see here in the picture that we're talking here about wind turbine. So the wind turbine are tested in the lab. So you either can scale it down and you allow air to go around this. You can even inject smoke to see what is the turbulence and what is the location of high pressure, low pressure, velocities. And so you can actually test all this. And also you can add sensors that is measuring dynamics, forces, right? Because forces are important to design material, right? Or select the material in these turbine blades, right? What will be the the deflection, the strengths, and all this kind of thing. So you are way better having a controlled experiment in the lab and measure every single parameter that you wanna measure, just to predict the performance. Because sometime when you are in the real field, you cannot control the parameters. So one of the very importance of the dimension analysis is understanding how you can design a controlled experiment in the lab. Okay, so I keep saying this over and over to all my grad students. When we are designing something in the research, we have to keep in mind, okay, what I'm going to measure and where I'm going to measure these. Okay, and if I measure this at this location, somebody else will come and say, oh, why selected in this very specific location, right? Why didn't measure here and there, right? So you have to really design your experimental setup, your experimental condition for this testing model, just to make sure that you are covering all the performance of the actual system. Okay. We are not going to build a power plant in our engineering lab, but we can build a small little component that is can be used, or the data or the findings can be used to design a full-scale component in the actual nuclear power plant, right? But it only depends if you run the right experiments with the right parameters, okay? And you make sure that you collected the right data to represent this actual performance, okay? It is extremely critical type of thinking when you are doing this, okay? I don't have to mention other application. Remember, like, the aerodynamics shape of these cars, like, sometimes, designers and artists, they go and carve, the shape of the cars based on the look, how it looks and stuff like that, but also they want to test it, right? So sometimes it is much more reliable when you are actually testing a prototype in a wind turbine or wind tunnels, okay? So even not a small scale model, you can even test the whole full scale model, but now you are measuring specific information that you cannot really get it while the car actually running. It doesn't mean that you are not testing the prototype in the real condition. You still can do this, right? But you are saving a lots of effort and time in modifications. So you can test like hundreds kind of models in the wind tunnel, and you are kind of optimize the performance, optimize the design and everything, and then you build the final prototype, which can be tested in the fields. Not only wind, but you can even do the same thing for, like, stuff that is subjected to liquids, right? Like, for example, ships, like the body of the ships, the weight and balancing, or loading the ships and stuff like that. You can actually test these in what we call it the water tunnel, or like, hydrodynamic tunnels here, okay? Not only applicable to system that is a mechanical system, but it can be applied to biomedical system, right? So you are not gonna, even though it's like you can have the same scale as a device, the biomedical device, but now the complexity of the testing is you cannot really test this on patients. So you have to really test this in the lab by simulating the function of the body's performance and how this system works, right? So the question we have to ask ourselves in this chapter is basically those 4 questions, okay? How many experiments we should do? Okay, so shall I run this experiment in the lab? How many times I have to run this experiment, and what kind of variables I should test? Okay, how many experiments for each variable? So if I want to test, like, the effect of the flow velocity, for example, okay, what kind of flow velocity ranges I have to test? Okay, and if I test it for the full scale model, how about if I have a smaller scale, like 1/10 of the actual design? I'm gonna test it at the same condition, or I'm gonna test it at different condition to simulate the actual performance. This is what we're gonna answer in this chapter, and what ranges, as I mentioned. Okay, in order to understand simply why this is happening, so let's consider here we have a very simple device, and this device is a very simple device called, like, a nozzle. Okay, so this is, and this nozzle is basically installed in a pipe. And this flow here will go through this nozzle. And because the flow will go through this nozzle, you will see, turbulence and eddies. Okay, we're gonna learn about this in chapter 6. But you can imagine now this nozzle, or this plate here. Okay, so this is a circular plate, circular nozzle. It's almost like a nose cone shape. So if you look at this, right, so this is something like that. Okay, so it is, so this is basically the nozzle I'm talking about here. Okay, and it is installed in the pipe, so the flow is going like this and going like that. And by going by the fluid flow going like this, the more the flow, the more these kind of turbulence and eddies generating, and the more that the pressure between the point here and the point here, right, it will change, right? There's going to be some pressure drop, okay? And how we know this is we know this because we apply like a simple, you know, momentum balance, right? We apply simple, like, you know, equation of mass and momentum balance. So we know that this pressure drop between point 2 and point 1, right? So this pressure drop here will be, you know, different if you have a different flow. So you have more flow, you will have different pressure drop, okay? Which mean different flow mean different velocities, right? How about if I test these for water and I test it for oil and I test it for, you know, other type of gases, right? So, you know, fluid density and viscosity also can affect, like, you know, these pressure drop. So it depends on the fluid type in these orifices, right? How about if I design these orifice? So this is the diameter of the orifice. If the diameter change, okay, or even if the diameter of the pipe change, right? So all these conditions will change the reading of this pressure drop, right? So the delta B between 1 and 2, right? So if I were able to measure this pressure, I will see that, you know, this variation of pressure will depend on so many variables, okay? So which means that in order to build a system or build a device, let's call this is, you know, nozzle flow meter. So let's say, for example, I'm designing this flow meter, right? And how I'm gonna design this, I will just basically, you know, put like a pressure gauge here, and I put a pressure gauge here. This is B1 and this is B2, right? And those pressure gauges, if you remember in chapter 2, it's kind of a dial, let's say dial like that, so I can see what is the pressure, so I can measure pressure. Okay, so by measuring B1 and B2, I can just say, oh, the flow rate is that much, or the flow rate is that much. You know, if the pressure B1 and B2 change, I know that the flow rate is that much. So I'm designing a nozzle to do this, right? So now if I want to design this, I need to know what is the relation between this pressure drop and the flow rates and other things, right? And how about if I'm testing this in a pipe that is 1 inch versus, like, you know, 20-inch diameter, right? So there's so many like data in order to create this, right? And if you want to do these experiments, okay, you will end up doing something like this, right? Of course, this is very simple, you know, analytical equation for that. And this is our Bernoulli equation between 1 and 2, neglecting the losses, let's say, right? So now I have B1 over gamma plus Z1 plus V1 square over 2G equal B2 over gamma plus Z2 plus V2 square over 2G, right? And point 1 and point 2 are almost like, you know, it doesn't have to be even horizontal. It's just like, you know, very close together, right? Just before the nozzle and after the, you know, just after the nozzle. So this is like, you know, can be the same kind of, you know, value, right? So which means that it is a pressure and velocity. So what is the relation between this velocity as well? Yes, energy. Yeah. So we can, you know, when we put, I don't know what does eddy current mean. Eddies, I mean, like, you know, these turbulence. Yes. Yeah. If this is what you mean, right? So these eddy losses, I don't call it eddy currents. You know, I think we'll talk about these eddies in chapter 6. So the losses, yes, if we consider the losses, we have to apply the energy equation and we put this, right? But even for with a simple analysis like this, just to give an idea about like what is the relation, what parameters are, you know, affecting this, right? What other condition that is relating V1 and V2? Anyone? What is other parameter affecting V1 and V2? Can I relate V1 and V2? You're just coming out of the midterm exam, right? Is there any relation between V1 and V2? flow rate. Okay, mass flow rate. Yeah, and okay. I mean, I don't know if this is. Yeah, I don't know if it's Q or equal Q, right? Because I didn't say anything about incompressibility here. Okay, please. So basically, I can say even conservation of mass, M1 is equal to M2. So it's rho 1, A1, V1 is equal rho 2, A2, V2, right? So it's just in general, right? Because rho 1 and rho 2 can be different if you have a gases, for example. So the gas density affected, by the pressure as well. So now if I make an experiment and I measure these B1 and B2 function of V1, so I know what is V1. Let's say, for example, I know how much mass coming in, so I know what is the density, and right, so I know what is V1. I can start plotting the relation between V1 and right, and this is only for the diameter of the orifice. So this diameter here, okay, is 3. I mean, like a 3, whatever unit is, right? Just like one, diameter. If I repeat the same experiment, but I change the diameter of the nozzle or the orifice, I will get like another data set, right? Of course, this is a line for the curve fitting of these points, right? And the same thing if I have a different diameter of this, right? And all this is for one fluid. Okay, and also for one pipe diameter, right? Right. So let's say this is a D pipe is equal a certain, meter or something like that, right? So in this case, we know that all these conditions can be changing, right? So I have large number of data and curve fittings and right. So I need to take, let's say, for example, like it's in order to build this curve, let's say 10 experiments. Okay. So I need for a different orifice here, this is a 30 experiment, and all this only for one density and one diameter. Now, if you're going to change the density of the fluid, keeping the diameter the same, so you're going to create another set and you do the different density and so on, right? And then you go back again and repeat this whole number of experiments, okay, for the same density, but now for different diameter of the pipe. 1 inch, 2 inch, 10 inch, 6 inch, and so on, right? So you can imagine the large number of data that you have to really collect in the lab, okay? And now we are talking about like economic value of this, right? Lab experiment is a much more expensive type of research you are doing. So if you are working on an analytical model or like, a computational simulation, of course, the computational simulation will cost money because the people are running this simulation, they have salaries, the computer they are using, the storage on the cloud, all these kind of, it costs a lot of money, right? So computational simulation will cost money, but it's nothing compared to running an experimental, program just to do the same exact, analysis, like, or, solving the same problem, because now you're going to build the experimental facility. You need more people, you need more equipment, you need to run this 4 times. So it's like, it's massive. So when you compare the amount of, money that you have to spend on an experimental research or experimental analysis, is going to be, much more than just a computational analytical type of solutions. Now, in order to reduce all this, you can just manipulate this Bernoulli equation. Okay, so when manipulate Bernoulli equation by just looking into, a way to, get this equation in what we call it a non-dimensional form, right? So I'm just getting B1 minus B2, and then divide by, half rho V square, right? And then, why I'm dividing this, because this is a dynamic head, right? So so basically I divide by this, and now I will just get this V in the other side, It's V square over V1 square, which is actually, this is basically an area over area, right? Now I'm converting the Bernoulli equation from this form to a non-dimensional, form like this. And now if you look at this, this parameter, you will see it is a non-dimensional number that has no units, okay? And instead of calling this pressure drop, we call it pressure coefficient or coefficient of pressure, okay? And coefficient here has no units. That means it's, it's a dimensionless number, okay? And now this, part here is D over D. This is basically like, a restriction coefficient or something like that, right? So we know what is the area, D1 over D orifice, right? And luckily, by doing this, you are actually converting all these three lines into one line here. So because now you don't care about how much is pressure over V. It's just like the ratio is just the same, right? So now we are converting this large number of data point for many curves into one single curve, okay? So whatever the pressure is over the velocity, and also whatever the ratio between, diameter and diameter of the orifice. For example, if the diameter of the, of the pipe is 1 inch and the diameter of the orifice is 1/4, that means it is, D1 over DO is 4, right? So how about if it's like 16 inches and the diameter of the orifice is 4 inch, right? So it's 4 again, right? So for all the D ratio is equal 4, you will find a unique number of the pressure coefficient. Okay, so the idea here is minimizing the number of experiments. Okay, so this is a general idea of the non-dimensional way of looking at the data, the experimental data. Now we are converting the problem from this problem here, that is it is a dimension depend on like the pressure difference, if it's like 10 kilopascal, 20, 30, 100, right, to a pressure coefficient here, right? And this pressure coefficient will be function of this diameter ratio. So we call this is a non-dimensional relation between these two parameters. Would we have it unit? If we rearrange the pressure coefficient to get a single velocity or area, would have the units. I don't understand this, but I'm trying. If we arrange the pressure coefficient, so okay. If we change it from this specific form, is that what you mean? Like A1 over A2? Yeah, like V1 over, yeah, we're gonna create a different non-dimensional group. Yes, I understand now your point. Yeah, so I decided to group the parameter this way, right? And actually, this is a core of today's lecture. Why we decided to, divide by half rho V square, for example. Why we decided to get the velocity V1 over V2 over V1 and stuff like that. Because we, I will, as I'm gonna explain later on, we have to agree all in our fluid mechanics community, all the scientists and researchers, about some kind of way of presenting these, right? So I'm not going to create my own way of presenting this, right? Or if I want to do this, it's going to be only for a new stuff. Like if I'm working on a new research or a new topic, yes, I can create my own number. I call it like Ahmed's number or something like that, right? But the idea here is you have to use what have the people in the past, like looking at this type of experiment or this type of analysis or this type of problem, right? This problem is a pressure drop and flow rates kind of thing. So it has a lots of people have done already this research, and we come up with a convenient non-dimensional parameters, right? So you have to really go along what other people are doing, because they spend all these times just to find out what is the most appropriate non-dimensional group, right? So I agree with you, Marcus, that it is all depend on your choice, right? And I have to say that this is all art. Like, you know, the experimental stuff and the way that you are actually doing the experiment, the way that you group this number, it is all has no, like, you know, of course you're gonna go with what is commonly used, right? But how about if you are innovating a new design, right? If you are making a new device that, you know, people are not tested these two relations before. So you have to really be smart around how can we repackage these parameters in a new parameter, and this has to be a unique parameter, okay? Because if you selected the wrong group, those data that you are talking about here will not form a line. It will be scattered, you know, data. Okay, so you have to be, you know, careful about this. So why we are selecting this? Because it's a very unique relation, right? And if you are, you know, if you are doing a new stuff, you're gonna play around. You're gonna keep changing these non-dimensional parameter and like making sure that at the end there is only one unique relation between one variable and the other variable. But this variable now is called a non-dimensional variable versus a non-dimensional other variable. Okay. I hope this answers the question. So now let's start by, there's so many methods for doing this. One of these methods is just like a mental exercise, like try stuff like this and, you know, art and just doing this, right? You can just look at all the parameter and try to combine them in whatever way that you want, right? But of course, we are not at this stage. We are just learning fluid mechanics, right? So we're gonna choose like a very simple method for this. So somebody who has like a very solid background in, you know, in this topic, and I want to just like get step-by-step type of analysis to really get the best, you know, solution. And this best solution can, or the first solution can be improved. Like once you get the number, you can actually play with this number to improve it a little bit, right? So we have to agree on that. So the first simple method is something called Buckingham Pi theory. Okay, and this is a Pi. This is sorry. This is a Pi theory. Okay. So I hope you still remember, like, you know, dimensions, right? In SI unit, we know the dimension is 3 dimensions: M for the mass, L for the length, T for the time. Right, so we know that, right? And we know that those are the basic dimensions. I hope this is, you know, very straightforward. Dimension of the pressure is a secondary dimension, because we know that the pressure, and again, this bracket here mean the dimension, like, you know, so the dimension of the pressure is mean, like, you know, the dimension of the force divided by the dimension of the area, right? So we call the pressure dimension is, you know, a secondary dimension, or a secondary value. So now F over A, F, we know F is mg, right? The mass times the acceleration, right? So, and then the area is length square. So we can put the, you know, the force as, this is a mass times acceleration, so L over T square, and then you divide it by L square, right? So at the end now, the pressure dimension is M divided by T square L, right? So we know the dimension for any secondary variables can be determined. Like velocity, for example, is L over T, the dimension of a length divided by the dimension of a T, okay? What is Buckingham Pi theory is telling you? Is telling you that if you have a group of variables, you have so many variables, this variable could be the main variable. Let's say, for example, the force acting on the wind turbine. Okay, so what will be the force, you know, or the torque of these wind turbine blades? Okay, it is affecting by the diameter of the wind turbine. It is affecting by the velocity of the flow. It is affecting. It is affected by, you know, the thickness of the blade. It is affected by the density of this fluid. It's, you know, so you can say that the main parameter, which is, let's say, for example, the torque. So this is a main parameter. It's function of other variables. Okay, as many as n variables. So it can be a general n variable. Okay, so n is a number of variable involved. Okay, m is the number of basic dimensions. So when you look at those variables and you present them in these four, okay, all of them will be function of these basic dimensions, okay? What is the maximum number of M? What is the maximum number of M? What is the basic dimensions? 3, right? It's M, L, and T, right? So the largest number of M is 3, right? So if this whole variable is function of M and L and T, that means the M is equal to 3. Some of the variable doesn't have to be, M, L, and T. It could be all function of L and T, depend on the design problem, right? But again, M is basically representing the number of basic, dimensionless, like, variables here. So, and N is a number of variables. So he's telling you that you can convert this equation, which is a main variable, as a function of this variable, but now in a dimension, like, it has every one of these parameters has a dimension, has a unit, right? Now we are converting this equation into a non-dimensional equation. And this non-dimensional equation, now it is called by, okay, so by one, okay, and by one here is containing main variable, okay, function of the other by 2 or 3 and 4, right, until to a large number, which is going to be N minus M, right? So the number of group that you can generate is going to be N minus M. So see how many variable you have, see how many basic dimensions you have in these variables. You subtract these values, you find out, yeah, it cannot be negative, no, right? So, but I will tell you, for example, like, imagine now we have only 2 variables, and those variables, like, function of M, L, and T. So those 2 variables now, 2 minus 3 is minus 1. What does it mean? Yeah, what does it mean? I have 2 variables. No, it's not wrong. It means that you actually can combine these 2 variables together, right? You don't need that many analysis to do, and you can create a ratio between these 2 variables, like, right? I think I have maybe a example like this, and this is actually a very good question. Okay, I can create like this variable, but now this by group is like, it's going to be only one by group that is equal constant. All right, it's not going to be function of any other by's. Okay, but the minus 1 doesn't mean anything. It just like mean that you are kind of overkilling the problem. Just the problem is very, it's just like 1 by, and this by is constant. It's just like, this variable here, rho v square over 2, or like d something, equal 5. So every time you are creating this group, the multiplication and and division is going to be ending up with constant number. Constant number means constant, 5, 6, 10, 100, 500, something like that. Okay, so just to, it's a very simple type of analysis, and it's very interesting type of analysis. So let's do one problem so you can understand the extent of this. Like, it's a very simple way of looking at this, but keep in mind, please, that it has a lot of art, right? So if if the problem itself is not telling you what to do, or what is the main variable and what is the other variables and stuff, it's going to be dependent on each of your judgment, right? So if I'm giving you a problem, like, for example, the senior design project, I'm telling you, oh, I have this, device, I want to just design this, right? Now you're gonna, you don't have a statement of a problem, right? You have to come up with your own type of judgment. What is the main variables, and how this variable is affected by what? Okay, So do you agree with me that somebody like, you know, will say, okay, I have this main variable f function of 4 variables. So now, you know, it's the total number of variable 5. Somebody else will come with, oh, actually, these main variables function of 7 variables, right? Including other factors, okay? Which one do you think is better? Which one do you think is the one who, you know, he knows, you know, these variables function of so many, or the one who is finding the right variable that is, or like smaller number of variables? Which one is better? Smaller number, anyone, fewer variables, problem trying to solve. Yeah, I like that, you know, it is depending on the problem, but also not every time fewer variables are good, right? Because you could be missing effect of something that you don't know. That means your design is poor. Your design is not capturing. Okay. How about for large number of variables? How about, you know, more? How about the guy who putting more variables? Is that good too? Yeah, it might be complicating it, right, Dan? Right, and I guess I agree with Owen. Like, you know, it's over more experience. Like, so we have to agree together. It's like you have to be more experienced in order to design the right. And this is what is different between a good designer and a good engineer and a bad engineer, in my mind, right? Because you guys gonna go all like, you know, after the graduation, and you're gonna get into different topics of your life, different fields, and doing different stuff that you might never seen it before, problem that you haven't seen it before. Okay, the good about like the way that if you really acquire the amount, the right amount of knowledge in your 4 years of undergrad, is to know how to relate things together, how to really, you know, simplify this big problem into a smaller problems, and then you solve each one individually, right? So it's all depend on like how good you are, what is knowledge you have, right? So sometimes you can come up with a problem and you really complicate it to the point that doesn't make any sense, and you're going to spend a lot of time and money and just to solve this problem, and it might be actually, you know what, those 2 variables that you added is like, you know, it's not affecting anything. But how are you going to know this if you are not a good designer, if you don't know what is the physics behind what you are doing, right? So that's why some of the engineer will be innovators, some of the engineer will be entrepreneur, right? Because they know how to really relate all these parameters, or they want to innovate, like, you know, create a new dimension of a problem, and then you apply some, you know, because, you know, scientists sometimes they tend to get more deeper and deeper and deeper to get more analysis, right? But engineer his main contribution is, we need to solve this, we need to really, right? So what we learned in the physics, how can we apply this in the reality, right? Okay, I need to close this valve here in this system here, right? What kind of, you know, condition I have to monitor for this, right? I'm not gonna go back and just do like a 1 year analysis just to come up with this decision. Sometimes you have to really get the decision on the spot, right? So again, the level of complexity, the level of analysis, the level of, you know, or the number of variables that you are selecting, and how complex the problem or how simple the problem is, right? It all depends, right? And there is no one answer, more variable or less variable. Sometimes the right amount of variables for the right amount of uncertainty that is allowable in your system. Okay, you're designing an aerospace component versus you're designing, you know, a plumbing system in your house, something like that, right? What will be the, you know, expected uncertainty versus, you know, in these 2 systems, right? So let's solve these problems. So again, as I mentioned, you know, sometimes those problems is very straightforward by just giving you a description of these problems. We're just making it simple for you. So he said, like here, how many groups of variables could be found in an experiment of a flow path sphere? This is the simplest, flow around bodies, right? Why? Because this is the simplest geometry you will ever have. Okay, this geometry is what? Is a sphere. And the sphere has how many geometrical parameters? One, which is diameter, right? Okay, so, or radius, right? So you have very simple geometry. Of course, car will have many dimensions. So you have all these dimensions. You have to really optimize all these dimensions. Okay, how about cylinder, for example? Or if you have a cylinder, it's two, the diameter and also the length of the cylinder, right? So the more complex the geometry, the more, complex is the design, the more complex is the problem, right? So this is a very simple sphere. And the sphere here is, has a diameter or a geometry D, and it's telling you that the force of the drag, this sphere is moving in a flow, or the flow is moving around the sphere. Same thing, right? Imagine now you are, simplifying a flow of an aeroplane, and you consider this aeroplane is just a sphere, right? Simple sphere, right? And the flow is going around this aeroplane. Now there is something called the drag force. What is the drag force? It's a resistant force, right? So flow going around the sphere, so it's going to be some drag for this flow, right? And he's telling you that this drag force here is function of the velocity of the fluids around this sphere and function of the density of these fluids. Of course, if you test the sphere in water versus you test it in in air, it's going to be different. And the diameter of the sphere, right? So it's giving you four, actually five parameters here. So FD, velocity, density, viscosity, and the diameter. Okay, how can we solve this problem? Okay, so I know that this is a flow over a sphere. Okay, if you remember, the main variable is function of the other variables. The other variable here is velocity, density, viscosity, and the diameter. So you remember the y equation. So this is basically your y equation. So the number of variable is use the time to solve this with me. Number of variables is no. The number of variables is 5. Why? Because this is the main variable, function of other variables. Okay, so those are the so this is a main variable because force is one of the variables we have. We're gonna measure it, so, right? So, but how much velocity change affecting the force and so on, right? So the number n is 5. Okay, now the number of the dimensions in this. So very simple. I can just start putting FD, and FD, the dimension here is, if you remember the force is mass times acceleration, right? Divided, right? So it's basically mass L T minus 2, right? So mass times acceleration is L over T, so it's ML T squared. How about, the velocity? The velocity dimension is L over T, so LT minus 1, right? How about the density? The density is kilogram per meter cube, so it is M L minus 3, right? How about the viscosity? The viscosity is, if you remember, it is Pascal second, right? So it's a pressure times second, right? So if you get the dimension of this, is going to be M L minus 1 T minus 1. So you can get the dimension of all the variables. The diameter, the dimension here is L, right? So what is M here? What is the number of M here? It's 3, right? And you don't have to have like all the 3 in every one. Like it's just like you look at all the parameters together and see, oh, you have M, yeah, I have L, yeah, I have T. Okay, so it's 3, right? So what is the number of group here? So the number of bi groups is what? So it's 5 minus 3 is equal to. What is this telling you? It's telling you you have bi 1 and bi 2, group 1 and group 2, okay? In order to generate these groups, okay, you will form it in a way that's bi 1 is equal function of bi 2. You're gonna convert equation 1 into equation 2, and equation 2 is a non-dimensional equation, okay? So now, in order to generate this, it's very simple analysis, okay? We're gonna select, okay, number of variable equal M. So we're gonna select number of variables equal M, okay? And those, we call it repeated variable, okay? So what is M in this case is 3. So I'm gonna select out of these 5, 3 variables, okay? None of them is your main variable. So 3 out of these 4 here, okay? So we're gonna select these repeated variable, right? Not including the main variable. So I'm calling this repeated variables, okay? So let's select, for example, here, right? Row V and D. How about if somebody else selected different ones? You're gonna come up with a different groups. That's it, right? And I will tell you at the end, whatever group that you are creating, you can manipulate it later on by doing simple mass relations. You know, square the group, or like reverse the group, or multiply 2 groups together and then just get another group, stuff like that. But I mean, like, you know, all the solution will be acceptable, and all the solution is kind of, you know, will lead to similar results, okay? So we are selecting 3 variables. We call them 3 repeated variables. The number here is 3 because, you know, the number of M is 3, so we're selecting the repeated variable. And in order to find out this group, to find bi 1, okay? So bi 1 is containing the main variable. Okay, so what does it mean? It means that this bi 1 here is your main variable. What is your main variable? Is FD, right? So bi 1 here, in order to create this bi 1, you get this FD, which is a main variable, and multiply it by these repeated variables to the power A, to the power B. Oops. Just multiply this variable to the power A, B, and C. And all A and B and C, I don't know. I just need to find out what combination of these, right, can generate the first group, okay? Given that I know I'm creating what we call it a non-dimensional group. What do you mean non-dimensional group? What does mean non-dimensional group? No units, which mean that M to the power 0, L to the power 0, T to the power 0. Agree with me? So at the end, this multiplication of these 4, the main parameter multiplied by the 3, they all have dimensions of 1, like there's no units. That means M has exponent of 0, L has an exponent of 0, T has an exponent of 0, okay? And just try to find out now, okay, from this equation. So what is the equation here? F here, the dimension of F is basically M L T minus 2. The dimension of density is M L T minus 3, but it's all to the power A. The velocity here is L T minus 1, but it is to the power B, and D here is L, but it is to the power C. Okay, now in order for this to be M to the power 0, L to the power 0, T to the power 0, I just need to find out A, what is A, and what is B, and what is C. I know that, you know, when you have an exponent like this, you know, the exponent will be multiplied inside, right? So if I know M has to be 0, that means what? See here, this is 1, right? M here, this is 1, so 1A, so plus A. B here, there's no M here, there's no M here. So this has to be 0, right? Which means that A has to be minus 1, right? So what is the value for A that it has to be like minus 1? Because I need at the end, when you multiply all these three variables, multiply by FD, you end up with a non-dimensional number, right? So A has to be minus 1. So the unit of this you know, group here has to be non-dimensional. Okay, I can do the same thing for, you know, for L, or let's say do it for T first, because it's very simple. T here is here, and also and only here. Here T here is minus 2, right? So this is minus 2. What else here? Oh, it's here minus 1 times B, so it's minus B. Anything else? No, this is all 0. That means B here is minus 2. Okay. How about L? The bar 0. So L here is 1. Are you guys following this? Please let me know. I'm sorry, I'm assuming it's okay. Perfect. 1 here, it's A minus multiplied by minus 3, right? Because L here is minus 3A. Here is B multiplied by 1, right? Plus C multiplied by 1 is equal 0. You know A already, and you know B already from the first two. Okay, right? So you can get C here is minus 2. So what is this telling you here? Huh? It's telling you simply that the group that you created by 1 here, this group that you created, which is by 1, is FD rho to the power A, V to the power B, D to the power C. A is minus 1, B is minus 2, C is minus 2. So what does that mean? It means that this equation, or this, sorry, this non-dimensional group is FD divided by rho divided by V squared divided by the diameter square. So by 1 here is this. So if you look at this, the, you know, FD over rho V squared D squared, this is a non-dimensional group. Okay. Is it clear, guys? Yeah, okay. So now how to find out by 2? Yeah, the rest, right? Because now we have by 1 including the main variables. We agree on that. This is the main variable. Now we already take rho VD. Okay, we take rho V and D. Now we need a group that contain the rest of the variables. So now we have viscosity, right? So we take already FD and by 1. Now we are going to take the viscosity, right? So to create by 2, it is a viscosity times rho times A, V times B, D to the power C. Okay, I'm gonna do the same exact thing, right? So viscosity here is ML minus 1 T minus 1 and MLT minus 3 to the power A L T minus 1 to the power B D to the power C. I can find out A, B, and C the same way, right? A here is minus 1, B here is minus 1, C here is minus 1. Okay, so which means that by 2 here is viscosity rho VD. Okay, so now I can write the equation. Okay, by 1 is equal function of by 2. By 1 we know it is FD, rho V squared D squared is equal function of mu rho VD. So I have only two group. Okay, so if I group these, if I get like what is rho VD or mu over rho VD, right? And in the lab, so I want to that is 20. It doesn't matter what the combination that make this parameter 20. Okay, so every time we are doing measurement in the lab, we are not going to do only the effect of the viscosity by itself. We are not going to do the density by itself. We are not going to do the velocity by itself. But we're going to create the effect of this whole group on the coefficient of, we call it here the coefficient of drag. Okay, the coefficient of drag here is coming from the force of the drag divided by rho V squared D squared. Okay, and when you do this testing in the lab, you will end up with some relations, but sometimes this relation could be look awkward on the graph, right? So there are some what we call it like characteristics of this pi. Okay, if you flip the pi, if you flip mu rho VD, you can convert it like this: rho VD over mu. Is it still dimensionless or not? Huh? Is it still dimensionless? Yeah, so right. So I can change the way it looks, right? Because I know that this is something called Reynolds number. And Reynolds number is a very famous number. Reynolds himself, when he investigated the effect of the density and viscosity and the diameter, he ended up with something called a certain number. Like if this number is below 1,000, the flow is like this. If the number is above 2,000, the flow is like this. So it's kind of very well-known number in the fluid mechanics. Okay, and if I, for example, here, FD rho V square D square. If I multiply by half, did I change anything? Is it still dimensionless or not? Right? No? Why? Yes, right? Because half is has no dimension, right? It's just a number, multiply by number or divide by number, right? So it should be dimensionless as well, right? But why am I divided by half? Because this is the kinetic, the dynamic heads. Because you remember the kinetic energy is like half mv squared, stuff like that, right? So it's basically you're trying to convert it into a way looking at typical type of parameters. Okay. If you square something, or if you take the root of this whole pi group, still the same, right? If you take the whole root of this whole group, it will keep basically dimensionless. So you can do a lot of manipulation, but making sure that it is still stay as a non-dimensional group. Okay. And that's why you will see the common fluid dimensionless number is, as I mentioned, Reynolds number. Okay, and you will see here the coefficient of drag. This is what we are talking about here for a sphere, right? As a function of Reynolds number. And you can plot this relation. So if you have a sphere, for example, this drag coefficient is 0.47. It's just like a very like unique number. If you for whatever fluid is density or velocity, you know, you keep playing with the experiments, and you end up with a coefficient of drag that is equal 0.47. How nice is that? Like, you know, it's a very nice unique number, right? So you can actually tabulate this in chart like that, in engineering chart that people can use, right? And you can change the, you know, the shape of this. Like you'll see here, those are the number in the left hand side here is showing the numbers here for different geometries. Okay, and also if you can select, you know, the Reynolds number, for example, you see the Reynolds number changing, the drag coefficient changing. So okay, so basically in this case for a sphere, this is what it is. You see here. And when we say, for example, 0.47 is like actually this line here that is horizontal here at a higher Reynolds number. So again, for example, in application of fluid mechanics, you know, many applications that is dealing with higher Reynolds number. So in this case, I can say, oh, it's actually constant in this range, right? But you have a unique relationship between the coefficient of drag and Reynolds number. Okay, and you see here the coefficient of drag here for a cylinder is a function of L over D. You see, because you might end up with in this parameter here, if it's a cylinder, you will end up with the same equation, but now you're going to add another variable here, right? So it's going to be like, you know, another group by 3 will be L over D. Okay, without even solving, right? You don't have to really solve to find out if you have an L, for example. Okay, can you find out what is a non-dimensional group? You have unit length L, right? Of course, you can just say, oh, L is going to be divided by D, right? Because D is one of the variable, the repeated variables, right? It's going to be the A will be 0 and the B will be 0. Only C will be -1, so it's going to be L over D. So from your practice, you can just look at the parameter. You can actually combine them, and you know from the dimensionless is going to be dimensionless, right? So these are the very important, type of conclusion about this. And you can see here, like, you know, the importance of this non-dimensional analysis is showing, you know, for example, here, a very simple analysis looking at a car design from the 19th century to now. It's like you'll see the drag coefficient changing with time, right? Because the shape itself that you are changing, right? So the drag coefficient is a function of how the shape looks like, okay? From a very simple like box, like, you know, into a what we call it a streamline shape kind of, right? And the drag coefficient keep reducing. This will affect the performance? Of course, it's going to affect the performance by a huge amount, right? Because the drag coefficient, the more drag, what's going to happen for moving cars? The more drag. Anyone? The more drag, resistance is more. Yes, the drag is resistant. Okay, but what will happen to move the car? Less acceleration. Sure. What else? Need more power. Need more fuel. Right? You need to burn more fuel to reach the same speed, kind of. Right? So yeah, less fuel. It's not fuel efficiency has nothing to do with the drag. Fuel efficiency has to do with the engine itself. That's a completely separate idea. We're talking about the engine itself now inside the car. That's a totally different design parameter that we have to evaluate. But for like, you know, for the same engine, let's say, but you're changing the shape of the car, you're gonna, need more power, more like, you know, consuming more fuel in this case, right? So so basically, like, you know, all these kind of type of analysis is very useful when you are designing stuff, when you're designing system and need to improve these systems. So the people are really good in this type of analysis. The people are really good as an engineer to design stuff, right? So the more people will be able to get out of the box and design new products. So those are the common variables or common non-dimensional parameters in fluid mechanics. And I have to tell you something, I didn't say that before, but like, people not just combining groups like, haphazards, right? I told you like Reynolds number is rho VD over mu. It's a very well common number available in fluid mechanics. And when you look at these ratio, rho VD over mu, you will end up understanding physics inside this. So if you consider rho velocity, the density and velocity times dimension, this is representing inertia, okay? And the viscosity is representing, viscous forces. So which means that Reynolds number, physical interpretation for this Reynolds number is inertia force versus viscous force. So as you can imagine, that the sphere that is moving, the inertia of the sphere is somehow related to the viscous force or the friction forces on the sphere, right? So these two ratio between inertia and viscosity is related to what we call it Reynolds number, okay? Mach number, right? So Mach number is basically ratio between the flow speed and the sound speed, right? For example, when you are talking about compressible flow, the airplane or the rockets and stuff like that, you consider like, Mach number is basically one of the variables that you're gonna end up with, right? The speed of the flow or the speed of the objects versus the sound speed, right? Froude number is talking about inertia versus gravity. It's U square over GL. And Froude number, inertia and gravity, you will see that many of the flow that is free surface flow, like rivers, flow of a free surface over dams and stuff like that, it will be affected by what we call it like, Froude number. Weber number is surface tension is playing a role here, right? So you will see a ratio between inertia and surface tension forces, which is all related to bubble dynamics and bubble formations and stuff in fluid mechanics, and many other, many other variables. I'm not expecting you to remember all these, but this is for different topic, for different subjects. Keep in mind that you're not going to look for something new completely, right? Unless you have a completely new phenomena that you are discovering. Or maybe you are discovering something as a combination of multiple phenomena, right? So you have to look for what is the most common non-dimensional parameter that you're trying to search and find out. Why? Because it saves a lot of effort. Like you don't have to really do the whole like large number of analysis after that you come up with this non-dimensional parameter, because some other people have done, the effect of Reynolds number, for example, on the sphere drag and so on. So you don't have to really, create your own number that has, different shape, but it's again, like what are you going to use it? Okay. You're trying to find out some reasonable number that is available, common number, famous number that you can utilize other people data. And that's the idea, right? You do experiment in the lab. Okay. So what? How other people use it? Okay. You have to make sure that you present the data in a way that other people can recreate these data or can use these data in their setup. You don't create data or experiments that it's only you that you can utilize. Okay, and this is what is a function and the engineer is doing. You want to make sure that when you are doing something, people can make use of it. Okay. Those are many numbers available. I'm just referring you to this table in your textbook, but I have it here as like even for heat transfer, you will see a completely different type of numbers here that you have to, like, for example, temperature ratio, right? Natural convection kind of velocity. You will see all these numbers in all topics that you study in engineering courses. So heat transfer. Heat and mass transfer courses, applied thermofluids, even dynamics, vibrations, like robotics, like any law, you will see that there are some, number that is, people are using, and these numbers or definitions or non-dimensional groups are widely used to present some physics. So every one of these parameters are showing some effects. So when we are saying, for example, high Reynolds number, that means we have high inertia versus friction, viscous friction force, which mean low viscosity, or sorry, low friction in this case. So higher Reynolds number here is, the inertia here is dominant forces, and so on. Okay. Limitation as dimension analysis, as I mentioned, I think you guys already figured it out, that it's all depend on experience, right? It's kind of an art that you have to really come up with this group and try to see how can you kind of combine this group in a way to do your experiments. So it is all by experience, but this experience will come from practice, from being involved in so many problems that you are solving, and try to try different things and make sure that, oh, I tried this, this flow around river in a corner of, like, passing through the through the river is making erosion in this river or this area. Now you know what kind of parameter you have to really select in order to do this, by looking at Froude number, for example, or and other things as well. Okay, I'm gonna stop here, and next time we're gonna talk about modeling and similarity of prototypes. Thank you, guys. You take care. Yeah, take care, guys. You're welcome. Take care. Have a good day.